All right. This is Thursday, May 6, 2021, AP Physics C. I have some students still preparing to take the AP test, and I wanted to try teaching how do you find the moment of inertia for a non-uniform density object. But first, in chapter 12, they have an example of how to find the moment of inertia for a uniform density object. And so what I've drawn here is a long, thin rod. I'm arbitrarily going to put the axis of rotation at the endpoint matching the example in this problem. When we have a three-dimensional object, a cube, the formula for the density of the cube is the total mass divided by the volume. And in high school, we use the symbol D for that. In college, we use the Greek letter rho to represent that. And so that's kilograms per cubic meter. When you only have a two-dimensional object, like a sheet of paper, so this is rho. We define the surface density, sigma, as being the mass of the sheet of paper divided by the surface area of that sheet of paper. When we have just a one-dimensional object, like a very long, thin rod, we use the Greek letter lambda to represent the linear mass density, and that would be the mass of the rod divided by the length of the rod. And so here's a little summary of that. Volume formula, mass over volume, whatever the volume expression is, surface, mass over the surface area, linear mass over the length, the one-dimensional length. So this is a problem where we're going to find the moment of inertia through this axis point. And in this first example, the density is uniform density. So it's the same density throughout the substance. The generic formula for calculating the moment of inertia for any rigid object through an arbitrary axis of rotation is the integral over the dimensions of the object of r squared times the differential element of mass, where r is measured from the axis of rotation to the location of that differential element of mass. All right, so in one dimension, this problem is going to simplify down to x is the one-dimensional variable. So r in three dimensions becomes just x. And the differential element of width that we like to use when we do integration starts off as the differential element of mass from this generic formula. We need to convert this little differential element of mass into a much more convenient differential element of width, dx. The way to go from a small amount of mass to a small amount of distance is through the relationship of the linear mass density that says, look, the fraction of the total width of this is the fraction of the total mass of this. And if I have just a little tiny rectangle of width, then that little tiny rectangle of width times the density of this substance is the little tiny amount of mass in this little tiny rectangle of width. I keep calling it rectangle because really this is one-dimensional, but it looks like a rectangle. Let's call it a rectangle. If I do the entire length x, of course that should be the entire mass m. If I do half the length x over 2, I should end up with half the mass m over 2. If I do little tiny width of delta x, which in pre-calculus would be delta with a triangle still, little width x, delta x, that would contain little amount of mass, little mass out of the total. Little width out of the total, little mass out of the total, related by the density formula. Great. So we replace integral of r squared dm. It becomes transformed into the integral from the closest point to the axis of rotation, which is 0, to L, which is the farthest point from the axis of rotation, of x squared times, instead of dm, now I can replace that with lambda dx. Lambda is just the linear mass density, the mass of the rod divided by the length of the rod. So being a constant, I can pull that in front of the integral symbol. There it is. When you do integration, you are taking the limit as your little differential element goes to 0. You're taking the limit of the sum of all the little areas under the curve. So that is what integration is doing. An integral, if I could spell it and write it, is the limit as this little piece goes to 0 of the sum of all the little pieces added together. So this is just one little piece, but the entire rod will be split up into all of these little pieces, and then each one calculated and then added together. That total is the integral in this problem. So now we have this thing in a form that a math person could look at and say, oh, hey, I know how to do this integral. So in general, there are indefinite integrals and there are definite integrals. Indefinite integrals, for example, the indefinite integral of x squared dx is x cubed divided by 3 plus some constant of integration. Okay, that's indefinite. A definite integral would be where we say, oh, the limit is, in this case, x starts off at 0 and it ends at x equals L, the length of the rod, of x squared dx. So in this situation, instead of a constant of integration, we still get x cubed over 3, but now we're going to evaluate it at x equals 0 and at x equals L and take the difference in these two results. So the integral of, from 0 to L, of m over L in front of things, because constants don't affect what goes on under the integral. So a constant like the linear mass density can be pulled in front of the integral sign. And here we're saying it's x squared dx. So it's going to be m divided by L times this being x cubed over 3 evaluated at x equals L minus evaluated at x equals 0. So maybe I should write x cubed over 3 evaluated between 0 and L. X equals 0, x equals L. Okay, so writing it again. M divided by L is the constant in front of the integral. Now I can even put in, I can pull out a 1/3. So times 1/3. And now in brackets, I evaluate the two limits. When x equals L, x cubed is equal to L cubed. And I've already pulled out the 1/3. Now subtract from that the evaluation of this integral when x is equal to 0. So subtract from that 0 cubed. Well, 0 cubed is still 0. So this term just goes away, 0. And now I'm left with m divided by L times 1/3 times L cubed. So let me rewrite that. 1/3 times m times L cubed divided by L. One of these L's cancel. And so the answer in this particular problem is 1/3 mL squared is the integral for a long, thin rod of mass m and length L through an axis of rotation located at the end point of the rod. And just to give you some confidence that, hey, I got that one correct, when you go to table 12.2 in our textbook and you look up what is the formula for the moment of inertia for a long, thin rod about its end point, the formula says, ta-da! Well, not that you can actually see it unless I zoom way in. It says 1/3 mL squared. And that's, where that came from. That came from doing this integral. All of these results in this table came from doing the integral. I'm grabbing a fresh sheet of paper. In this particular exercise, the goal was, how do we do an integral when it is not a long, uniform, thin rod? Oh my goodness. So we're going to attempt to do it for a long, thin rod, but this time the density varies with position. In fact, it was a AP test question. Let me pause. That's odd. It says I've recorded nothing. Okay, so I just looked it up. On the AP Free Response 2021 Set A, they gave a problem that said, what if the linear mass density is not a constant, but it varies depending on the value of x? And that once again, we're going to put the axis of rotation on the left end of this rod. The rod has a length L. And what this says, strangely enough, is that when x is equal to 0, there is no mass here at the very tip. It's actually a value of 0. And a way of explaining what does this look like, a top-down view would show that this is a triangularly shaped object, perhaps. But this is this top view, and here's the side view. So what we see is just a one-dimensional object because the axis of rotation has all of the mass in this one plane. If we look at the top-down view, the axis here is everything is rotating about it like this, if that makes sense to you, okay? So if this pen cap represented the object, in this top view, it's rotating like this about the axis of rotation. In the side view, it's perpendicular to the plane of the paper, rotating this way. All right, so they're giving us a formula that shows how much mass there is as a function of x. So x is still going off to the right. And what we have going on here is as x goes to L, the density becomes 3 times m divided by L squared times I'm sorry, I said that wrong. 3 times m divided by L cubed times L squared at the very end. So 3 times m divided by L is the mass at the very right end of this object, and 0 is the mass of this triangle at the beginning of this triangle. Okay, so it varies, and it goes as the square of the distance. So maybe triangular shape isn't quite right, but good enough. Okay, so we still have a little differential element of mass, of width, dx. We still have the formula for the integral of r squared dm, where r becomes x in this one dimension. We still have to convert the little differential element of mass contained in this thing into some function of x. But in this case, it's not the simple one that it was before, where dm was equal to just some constant times dx. Now that value, oh man, depends on how far it is. And since the period's ending, let me see if I can really scrunch through this quickly. So dm is equal to gamma times x squared times dx. And gamma is a constant. So the integral I becomes the integral from 0 to L of gamma x squared times x squared times dx. And so gamma from 0 to L of x to the 4th power dx, which becomes 3m over L cubed times 1/5 times L to the 5th power minus 0. I'm just doing this rapidly to finish it up. So this becomes 3 times m divided by 5 times L cubed times L to the 5th power, which becomes 3/5 times m times L squared. And I scribbled down, they said show that I equals 3/5 ml squared. So this is what you were supposed to do on that AP test question.